Hey guys, we're about wrapped up with our discussion on surface currents. We just have a couple unanswered questions on gyres, and you already have all the tools necessary to answer these, right? All that you know about pressure and Coriolis effect, how all the wind patterns move in the atmosphere. So no slides needed for this one. I'm just gonna see if I can't find somewhere comfortable to sit down. So grab your notebook and we'll see if we can't dig in a little more on why those currents travel in a circle and also what makes those boundary currents so weird. So stick around and I'll see you here in a minute. All right, hey guys. So like I said, this is gonna be a bit informal. I'm just kind of hanging out here next to this little pond. And all we need to do is get into the particulars of why those gyres are shaped the way they are. Remember I asked you, why do those currents travel in a circle? So we know that these gyres are wind powered and they're shaped by Coriolis and pressure. So you're probably starting to put these pieces together and it may seem like this makes a bit of sense. But we're gonna get into the exact mechanisms of how this works. So the first thing is I had shown you a figure some time ago of when the wind blows over the surface of the ocean, that mass transport, that total mass transport actually moves at a 90-degree angle. And again, you may have already figured out, yes, that has something to do with Coriolis. In fact, that 90-degree angle is to the right in the northern hemisphere and left in the southern hemisphere. So let's figure this out exactly. So what we want to say is, all right, let's pretend we have a box in the ocean. So I'm going to go ahead and let's put a box up here. All right, so this is, remember now, this is still the surface ocean. So this is just an imaginary box. The top is the very surface of the ocean and the bottom is down a little bit. And then I'm going to divide this box into layers. So I'm going to basically slice the ocean into layers. So again, the top is the very top, and then as you go down, just a little bit more. And the reason I'm doing this, let's go ahead and put an axis in there. So, right up here is the surface of the ocean. And if I have the wind going in this direction, I'm gonna draw a big arrow here, right? This is the wind going in that direction, across the ocean. Well, what's gonna happen? Well, we already know that if a movement is pushing this surface layer a little bit, it's gonna wanna curve, right? Because of that Coriolis effect, it wants to curve. So this first surface layer wants to curve a little bit this way. All right, and as it turns out, that's actually about a 45-degree angle. Well, because I've cut the ocean up into layers, we can now think of, all right, well, this top layer is moving in this direction, and the one below it is going to want to curve just a little bit more. All right, and you can see where I'm going with this. Then the one below it curves just a little bit more this way, and this one curves. So we start to get this almost spiral. Well, it's actually called a spiral, but not in the sense of it moving in a spiral fashion. It's just that every layer moves a little bit to the right or left than the one below it. So going down in the ocean, this is called the Ekman Spiral. All right, Ekman Spiral is each layer successively turning, again, in the northern hemisphere would be a little bit to the right, and in the southern to the left. And what this means, actually, if you go all the way down to the bottom, you could actually have a current going in the opposite direction of the wind because of this effect. But overall, the important thing is if you take all of this mass, because again, each layer is going to be a little bit less than the one above it, that means all of this mass, right? Oh, this is a terrible arrow. All of this mass, I'm going to fix that. Let's just fix that. All of this mass, anyhow. There we go. Is moving at this 90-degree angle, all right? And that is something called Ekman Transport. In Ekman Transport, the surface current will move at a 90-degree angle from the wind current, all right? So we know that. So we're going to take this information and we're going to apply it to our gyres. So let me go ahead and get rid of all this. And wait for it. So I'm going to get rid of these, all right, and I'm going to pull up a picture of the Atlantic, all right? So here's the Atlantic Ocean, and right about, so down here at the bottom, all right, this is the equator down here, so I'm just going to put equator, all right? And then right about here, oh, maybe I should have done this with more appropriate lines. This is about 30 degrees north latitude. All right, and then 60 is up here somewhere. Let's see, where's Iceland? So it's probably right around here. Don't quote me on this. But anyhow, the important part being is remember these surface winds. And we already know that the surface winds are going to travel like this, right? So between the equator and 30 north, they travel south. And between 30 north and 60 north, they're going to travel northeast. So what we want to do is we want to take these surface winds and we're going to start to figure out the currents below them. So like I just showed you, if you have surface winds going in a certain direction, the mass transport of the current is going to move at a 90-degree angle to those surface winds. So here we see our 90 degrees, right? And so that is that mass transport, and that's because of Ekman Transport and Ekman Spiral. Well, that's great. So we have currents now. Now maybe it seems a little strange that they go in a circle because based on our planet, they should just go across opposing each other. But let's do something. Let's pick a point out here in the middle of the ocean, all right? And what do you see? Well, you see at this point, we have currents going this way and currents going that way. Well, currents can't just butt up against each other, so something has to give. Something has to happen. And what's going to happen is they're actually going to push against each other and bump up. So what you end up with is out here in the middle of the Atlantic, you end up with a hump. All right? So there's a hump of water. And it actually occurs out in the middle of the ocean. Well, okay. Now, based on something else you guys know about hydrostatic pressure, if this is my height of water in these two places, right, H1 and H2, well, we know that the pressure 1 is going to be greater than the pressure 2. And based on our previous discussion, we know that mass moves from high pressure to low pressure. So it's going to want to push apart. So you can see what we have. We actually have the Coriolis effect pushing water towards each other and now pressure pushing it apart. So what's going to happen is it's got to go somewhere. This is mass. It can't just disappear. So what's going to end up happening is these currents are going to go and they're going to have to travel around that hump. All right, they're going to have to travel in a circle. And this is where that circle comes from. So gyres are wind-driven movements of water, and they're shaped by Coriolis and pressure. So Coriolis is going to want to make them curve to the right, again, the northern hemisphere because we're in the North Atlantic, and then that pressure is going to oppose it. So they're not going to just butt against each other. They're going to have to move around that center spot. Okay, so that answers one question. Why do they move in a circle? But there is something else a little weird. So now we want to talk about these boundary currents, because we already said that, you know, you take this boundary current on this side, so this is the Gulf Stream, and we know that's that western boundary current that's very narrow and deep and very fast, a lot of mass movement. And then on the other side, right, you have a more diffuse current. You have an eastern boundary current. It's a bit shallow and spread apart. So let's see if we can't figure out why this happens. All right, let's get rid of this. And something else you guys remember about Coriolis is that the effect is greater the further you get towards the poles. So I'm going to go ahead and draw my 30 degrees back in here. All right, 30 north. And like I said, 60's up there somewhere. So we know that the Coriolis effect is greater in the north. So what happens is those currents, so say this is the Gulf Stream, it moves to the north and starts to curve around. Well, because that effect is so great up here, it's really going to want to turn soon. It's going to feel that pull of movement. However, the current that comes back across, it's a little lazier. It doesn't feel that effect quite so much, okay? Actually, I guess I should draw this down here. It doesn't feel that effect quite so much. So it's going to move along the equator, and it's not going to need to turn. So all that water is going to start to pile up. So let me show you another figure. Let's get rid of this. And let's pull up another cross section. So you remember my cross section before? Well, picture this all the way across the Atlantic. So over here on one side, you know, we can call this the east coast of the US, and then over here, what do we have? We have like Spain, right? So what ends up happening, if this is our hump, right? This is our hump in the middle of the ocean, and we know that we have pressure pushing down on the sides, all right? And Coriolis wanting to make these curves. Well, what ends up happening is you can see this hump is actually pushed a bit westward. So what we end up with on one side is this really deep ocean river, okay? So this current, is all this mass has to be in this very narrow section of current. And then as it comes around and that Coriolis effect wants it to start turning sooner, well, now on the other side, you end up with this really broad, like we said, diffuse current coming back the other direction. So then what you can see is that hump's not actually in the middle of the Atlantic, it's actually pushed over a bit because of that Coriolis movement. And that gives us these eastern and western boundary currents. And again, the transverse currents just sort of connect the two. So understanding why you have those specific nuances, if you will, about the eastern and western boundary currents is important. All right, so now we've answered our questions, right? We now know why these gyres travel in a circle. They are wind-driven movements of water shaped by Coriolis and pressure. And we also understand why these boundary currents have the specific characteristics that they do. And this can be applied in both the northern and southern hemisphere. In the southern hemisphere, again, Coriolis just works the other direction, but because you're going the opposite direction for poleward, we still get that desire to curve back sooner, and you still have that same characteristics of eastern and western boundary currents. And that's it. That's pretty much a wrap for our surface currents discussion. We are going to get in a little bit more. Your last lecture for the module is about climate. You know, we've already seen how the ocean and climate interact, you know, how these massive surface currents move global heat around the planet. So here you go. Before you get to watch the next lecture, I have 2 more questions for you to finish out this module for class participation. So what I want you to tell me, and this is just your best guess, again, you don't have to look these up, I want to know, why do we have seasons and why do we have ice ages? Why do you think we have those two? So go ahead and answer those. I'll make those due Tuesday by midnight, and then I'll hopefully have the answer for you on Wednesday. So think about it. Go ahead and do the readings up to this point, get ready for the next video, work on those homeworks, and remember, by the end of this week you have to let me know if you want to stick with your homeworks or take the exam. So I'll see you guys next time.